Hey guys, I'm sure you are super excited to be watching this fun math video. And since I'm in Appalachia, I figured that this was probably the best way for you guys to get the information. If we think about what we learned last class, we talked about all the reciprocal and Pythagorean identities, and today we are really building off of that. Today we're going to be verifying or proving those specific identities. So if you look at your note handout, I think that the 4 different guidelines that we have written out can be very, very helpful, especially if we go ahead and we take a look at this first one. Our goal today really is to get the 2 sides of the equation to be the same. So the way that we are going to go about doing that and meeting our goal, the first thing here, it says work with one side of the equation at a time. And I think this is really helpful. In fact, most of the time we only need to change one side of the equation. And I normally think it's easiest to work with the more complicated side first. The reason being it's easier to make something that is complicated into something simple. It is much more difficult to take something that is already simplified and try and make it more complicated. So our goal today, we're going to look for opportunities to factor an expression, add fractions, square a binomial, etc. We're going to look for opportunities to use the fundamental identities. And one reason that I think today's stuff can be a little bit easier than what we did last time is we already kind of have a hint as to what we need to do. Because if we look at the other side of the equation, we know that somehow I need to turn everything on one side of the equation into the same trig functions that are on the other side of the equation. And if nothing else is helping, we can always try converting things in terms of sine and cosine. So we're going to start here by looking at number 1. So if you look on your handout, you can find number 1. And the very first thing I'm going to go ahead and do here, I'm going to actually draw a line that is just separating the 2 sides of the equation, and that's just reminding me that I am really doing 2 different problems here. And the nice thing about the problems today is there are multiple ways that we could do this. So I'm actually going to demonstrate this with the first problem. I'm going to show 2 different ways we could go about solving it. The first way that we could solve it, actually regardless of either way we're solving it, I think we would all agree that the left side of the equation definitely looks more complicated than the right side of the equation does. So what I'm going to go ahead and do here, I am going to look at the top, the numerator of the left side, and secant squared minus 1 looks pretty familiar to me. In fact, it pretty much looks like one of the trig identities we talked about. And so off to the side here, and I think this is helpful if you do this as well, I'm just going to write a reminder to myself that we learned that tan squared plus 1 equals secant squared. Now, obviously it doesn't look identical, but I really need to think, how can I somehow make this equation look like secant squared minus 1? And so what I'm going to do, I'm going to go ahead and subtract 1 from both sides. So I end up getting secant squared minus 1 is equal to tan squared. Now, what that means we can do, we can actually take this tan squared and go ahead and substitute it in for secant squared minus 1. So I'm going to go ahead and do that to make the left side of the equation get a little bit simpler. So I'm going to go ahead and write here tan squared over secant squared. And I'm really just not even going to mess with the right side of the equation yet. Now we may remember that tan squared is actually equal to, tan is actually equal to sine over cosine. So if we have an exponent in there, this same exact identity applies. We're just going to make it sine squared over cosine squared. So I'm going to write sine squared over cosine squared over, we learned that secant is the reciprocal of cosine, so I'm going to write this 1 over cosine squared. Once again, I'm not messing with the right side of the equation at all. Now at this point it looks a little bit complicated. However, we know that when we are dividing by a fraction, it really just means that we are multiplying by the reciprocal. So I'm going to think of this as sine squared over cosine squared times cosine squared over 1. And we can see our cosine squareds cancel each other out, so I am just left with sine squared, which magically what was on the other side of the equation. So at this point we are done because we have an equation that says sine squared equals sine squared. Now, on a problem like this, it's a little bit different than what we're used to because the actual final answer is not really what is that important. It is all the steps and all the work that we've been showing. So for those of you that hate to show work, unfortunately, that really is the important part of the day. Okay, so now I want to go ahead and show you that we definitely can solve these problems using different methods. And you don't need to write this out if you don't want to. If you want to, that's fine. I know I didn't give you a ton of room to do that, but I just want to show us that there are multiple ways to get to the same answer. So I'm going to go ahead and divide everything in the numerator by secant squared. And I know I can do this because secant squared is a monomial, so I can just divide everything in the numerator by that number. Or in this case, it's not a number, it's just a term. I know secant squared divided by secant squared is 1. And 1 over secant squared is cosine squared. Now this also looks really similar to one of the Pythagorean identities we learned, so I'm going to go ahead and write that off to the side. So off to the side here, I'm going to write sine squared plus cosine squared equals 1. And this is kind of random, but I just want to remind us that whenever we are writing a trig function, we always need to have the angle written afterwards. So if we look at this, I know that I need it to be 1 minus cosine squared, so I'm going to go ahead and subtract cosine squared from both sides. So what this means is that I can go ahead and take sine squared and substitute this in for 1 minus cosine squared. So when I go ahead and substitute in sine squared, I end up getting sine squared equals sine squared. I actually think that this is easier than the previous way that I solved. However, the whole point is it doesn't matter. We all think in different ways. So whichever way you think is easiest will probably get you to the right place where I need to get both sides of the equation set equal to each other. Okay, so let's go ahead and take a look at number 2. Now if we look at number 2, we can see that the left side looks more complicated once again. And honestly, the reason why the left side looks more complicated is because I am adding two terms together, so we have a binomial. I should kind of think in the back of my mind, I know that when I'm done with simplifying the left side of the equation, that it should be in terms of secant. And the reason why I know that is because we have secant on the right side of the equation. So I'm going to go ahead and split this up. Now, when I'm adding two fractions together, we really need to try and figure out what would be our least common denominator. And a lot of times when I don't know what our LCD should be, I'm going to think of it as just multiplying those two denominators together. So if we look at this, I know for this very first fraction, I need to multiply. Let me change my color here. I'm going to multiply by 1 plus sign over 1 plus sign. So I'm going to get 1 plus sign over 1 minus sign squared. And 1 minus sign squared is what I get when I actually FOIL those together. Now on the second term, I'm going to multiply by 1 minus sign over 1 minus sign. So I end up getting minus 1 minus sign over 1 minus sign squared. And the reason why this is nice is now I have a common denominator, and that should be a plus in between there. So I can go ahead and just combine all of my like terms in the numerator. So if I'm adding my like terms together, I actually have 2 over 1 minus sine squared. And this should kind of give us a hint that we are on the right track, because if we look on the right side of the equation, we have 2 secant squared. So we knew that we needed to get a 2 somehow. Now I'm going to focus on the denominator, that 1 minus sine squared. 1 minus sine squared once again looks like that Pythagorean identity. And you'll notice those keep coming back again and again and again. So off to the side, I am going to go ahead and write sine squared plus cosine squared equals 1. So I know sine squared plus cosine squared equals 1. And by the way, it doesn't matter that we're using alpha this time instead of theta. It really is just representing that unknown. So I know in this case to get 1 minus sine squared on one of the sides, I'm going to subtract sine squared. So this time, when I'm substituting in, I'm going to take cosine squared and substitute that in for 1 minus sine squared. So I'm going to go ahead and write 2 over cosine squared. Now, we don't have our two sides that are equal to each other yet, but I know 1 over cosine is equal to secant, so 2 over cosine squared is equal to 2 secant squared. Now we have both sides of the equation looking exactly the same, so we have solved this problem. Okay, so we are moving on to number 3. If we look at number 3, this time both sides of the equation look a little bit more complicated, but I'm really going to focus on the left side again. And the reason why I'm choosing the left side is that we have fractions and things that are being added, so I think that makes it a little bit more complicated. This is very similar to our first problem where there are multiple ways that we could solve this. I'm going to go ahead and just think of it as dividing everything in the numerator by that term in the denominator. So I'm doing sine divided by sine and cosine divided by sine. We know anything divided by itself is 1. And if we look back at all the reciprocal identities that we used last time, cosine divided by sine is cotangent. At this point, both sides of the equation are exactly the same, so we are done. When we look at number 4, I think number 4 is the most difficult problem we've done so far. And the reason is I don't think either side is very simplified. However, if I had to choose, I would choose that the left side is more complicated because our denominator is a binomial. On the right side, since we have a monomial in the denominator, I could just divide everything by sine and we could simplify it from there. On the left side, I can't do that. So I need to think cotangent squared. Where have we seen cotangent squared before? And we have seen it in one of our Pythagorean identities. So off to the side over here, I'm going to go ahead and write to myself that 1 plus cotangent squared is equal to cosecant squared. And if I needed to get cotangent squared all by itself, I would subtract 1 from both sides. And what makes this complicated in my mind is the fact that we are really used to substituting one term in for two terms, and it makes sense why that would make something more simplified. This time it's kind of strange because I'm substituting in these two terms in for cotangent squared. However, if we actually look at those two terms, the reason why it can be helpful is because that fits our difference of squares pattern, and we can go ahead and factor it, and that's going to help us in our process of simplifying this. I went ahead and substituted cosecant squared minus 1 in, and now what we can do with that, I can factor it to be cosecant plus 1 times cosecant minus 1 over 1 plus cosecant. And even though these two terms look a little bit different, I know that I can actually cancel out these two terms because they are exactly the same. So I am just left with cosecant minus 1. Now this does not match what is on the other side of the equation, so I am going to have to do a little bit of work on the other side of the equation as well. I'm going to go ahead and take that 1 minus sign in the numerator and split it up, so I'm dividing both sides by sign. We learned last class 1 over sign is one of our reciprocal identities, so I could just think of this as cosecant. We know anything divided by itself is 1, so in this particular problem, I end up getting cosecant minus 1 equals cosecant minus 1. If we take a look at number 5, it looks scary and intimidating because we have all this stuff going on. But if we actually look at it, we know that the right side of the equation looks pretty simple. And even though there's a lot of stuff going on the left side, I'm underlining really the only 3 parts that we need to worry about. So on this problem, I am going to start with the left side of the equation, and then we'll see if somehow that turns into cosecant squared. So I'm going to start at this first section, the cosecant times cosecant minus sign. When we go ahead and distribute cosecant to both of those terms, I get cosecant squared minus sine cosecant. And we'll talk about sine cosecant in a moment. Now I'm going to take a look at this second term, and I'm going to think of this as sine divided by sine minus cosine divided by sine. You guys may be noticing that we are using a lot of the same, ways to, or strategies to solve these over and over again, and that's going to be true in your homework as well. So I definitely would make sure that I use my notes while I'm going through my homework. Last but not least, I have this cotangent all by itself, and I'm just going to go ahead and leave it for the moment. So now I'm going to try and simplify everything on the left side. And the first thing that I want to point out is this idea of sine cosecant. These are actually reciprocals. And one thing we may remember about reciprocals is that the product of any 2 reciprocals is always 1. And if we think about like 1/3 and 3, if we multiply those together, we get 1. If we did 3/4 times 4/3, we would get 1. So I'm going to think of this as cosecant squared minus 1. Sine over sine is equal to 1. Cosine over sine we know is equal to cotangent. And then I have that cotangent that's in the original problem as well. Now if we take a look, we still have a lot of stuff going on, but we may notice the 1's actually cancel out, the cotangents cancel out. So on the left side of the equation, we are just left with cosecant squared. And guess what? That's what we had on the right side of the equation as well. Since our 2 sides match each other, we know that we are done. Number 6, we have secant to the 4th minus tan to the 4th equals 1 plus 2 tan squared. I think both these sides look equally complicated. However, the left side of the equation may fit a pattern that we're used to. In fact, if we look at this, it is our difference of squares pattern. So I'm going to go ahead and write this as secant squared minus tan squared times secant squared plus tan squared. And so if we take a look at this, we definitely see some tan squareds, but probably the thing that we need to think about here is how can we somehow write secant squared in terms of tan squared. So I'm even going to write that out over to this side here, just so we have that written down. So how can I write secant squared in terms of tan squared? And the reason why we're thinking about this is we know we need to get both sides to be equal to each other. And on the right side, I only have tan squared. So in order for them to be equal, on the left side, I need to get rid of those secant squareds in some way, because I should only have a number and tan squared in my final answer. The other thing that we might notice when we look at this is that secant squared minus tan squared actually fits one of our Pythagorean identities. We know that that is actually equal to 1. So I can think of this as 1 times secant squared plus tan squared. And this is really what I'm going to think about. How can I write secant squared in terms of tan squared, like we talked about earlier? So the way that I'm going to do this, I'm going to take secant squared, and I know secant squared is equal to 1 plus tan squared. And then I still have that tan squared over there. And all this idea of the secant squared being equal to 1 plus tan squared and secant squared minus tan squared equals 1, those all relate back to our Pythagorean identity. The better we know our identities, the easier these get. Now if we look at this, I can just add my like terms together. So I get 1 plus 2 tan squared, and that's what the other side of our equation is equal to. So I'm going to write equals 1 plus 2 tan squared. This is a really good example of a problem where using the information given to us on the right side of the equation can definitely help us out in knowing what we want to do with the left side of the equation. And last but not least, we are on our final problem. Secant plus tan equals cosine over 1 minus sine. Now, some of you might think that the left side is the most complicated because we have 2 terms. I am actually going to think about it in the other way. I think the right side is the most complicated. And the reason why I think that is because we have that fraction. And the first thing I want to do is create a monomial denominator. So one thing we might notice about 1 minus sine is it kind of looks like 1 minus sine squared, which is a Pythagorean identity. So what I'm going to do here, I'm actually going to multiply it by 1 plus sine over 1 plus sine. And the reason why I'm doing this is that gives us that denominator of 1 minus sine squared. The reason why I can multiply by 1 plus sine over 1 plus sine is I know anything over itself is just 1. When I distribute that cosine, I end up getting cosine plus cosine sine. If we know our Pythagorean identities really well, which we should at this point, I know that 1 minus sine squared is actually cosine squared. So I'm going to go ahead, and now that I have a monomial in our denominator, I am going to split up the numerator and divide both of those terms by cosine squared. And now we can actually simplify. I know that cosine over cosine squared is just 1 over cosine, and cosine sine over cosine squared would become sine over cosine. Our 2 sides of our equation still do not match though, because we know the left side currently says secant plus tangent. But some stuff we do know, we know that 1 over cosine is equal to secant, and we know that sine over cosine is equal to tangent. So in this particular case, I end up getting, this will look kind of weird with my writing here, but that's okay, secant plus tangent equals secant plus tangent. So assignment number 2 on page 363 is your one assignment for the evening. You guys do have some time to work on it in class right now, and if you want to work with a partner, that is fine. I think it would be really helpful if you worked on this right now with someone, just so you could kind of bounce your ideas off of each other. Also, it'll give you a chance to just have something to look at because you won't finish all of it. So then when you get to working on it over Thanksgiving break, it won't seem so overwhelming and it won't seem like we did it 10 years ago. So the day we get back from break, I know it seems like a long ways away, you guys are going to be turning in 2 assignments for me. I'm going to be collecting assignments number 1 and assignment number 2. So those are the 2 things that are due when we get back from break. I would also expect to be ready to have a quiz. The other thing I would encourage you guys to do over break, if you go onto Myolu Studio, I do have like a final review type packet and suggested problems listed like under the tab that talks about semester 1 final. Our final is going to be here before you know it, so go ahead and feel free to download all that stuff. And have a great Thanksgiving. That's about it. I will see you when we get back. Bye.